Hello everyone, welcome to the course Semiconductor Devices and Circuits being held on NPTEL. This is the live problem solving session for week 4 of the course. I am Mayank Goyal. I am a research scholar in the Department of Electrical Engineering IIT Bombay. This course is being taught by Professor Sanjeev Sambandhan, who is a professor in the Department of Instrumentation Applied Physics ISC Bangalore. The, the course plan for this week is recombination generation, charge transport, and continuity equation. This tutorial is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So first we will be doing some lecture recap for this week's classes. So last week we had studied the semiconductor about electron and hole concentrations at equilibrium. So this week we will study what happens when they are out of equilibrium. So that is how carriers are generated and annihilated. So generation is called carrier creation is called generation, in which an electron is excited from valence band to conduction band, and this creates electron hole pairs from neutral species. This increases free carrier concentrations. In recombination, the electron in from conduction band recombines with the hole from valence band, which results in annihilation of free electron hole pairs back into a neutral state. This decreases free carrier concentrations. So now there can be different type of transitions. The main one is band to band transition, which are direct quantum jumps, where the a direct transition of an electron across the entire band gap. The trigger can be thermal energy or photon interaction, which provides a massive energy spike that is required to jump the entire band gap. This leaves a mobile hole behind upon generation and emits a photon upon recombination. It relies on uninhibited energy exchange, serving as the baseline mechanism for carrier dynamics. Then there can be intermediate states, which are called traps, and they are called RG centers. So they act as stepping stones. So traps are defects. So doping or crystal defects create trap states, ET, deep inside the forbidden band gap. The advantage of trap states is that the energy jump needed to reach a trap is vastly smaller than a direct band-to-band jump. So to go from valence band to trap state or from trap state to conduction state, you don't need much high energy. Don't need much. You need a much lesser energy compared to direct valence band to conduction band. So transitions occur as a two-step process. An electron occupies the trap state, then subsequent state transitions to the final band. What it does is that it leads to a significant increase in carrier count by lowering the energy barrier for transition. Now we can have exciton. Now we come to excitons, which are electrostatically bound pairs. So an excited electron and hole becomes coupled. They are mobile and diffuse through the lattice, but are not completely free from each other. So the electron or hole themselves are mobile individually, but they are but they are experiencing the Coulombic forces of each other. So they are moving like a pair. Because they are bound, the exciton has zero net charge. Forming an exciton is an effective loss of charge carriers. Then there can be Frankel excitons. They are tightly bound pairs with smaller radii. They are dominant in materials with low relative permittivity, such as organic semiconductors. So now there are multiple generation recombination processes, such as impact ionization. In impact ionization, a high velocity electron, which is driven by a high electric field, collides with the lattice. The kinetic force strips an electron from an atom, which creates a new pair, electron hole pair. Then there is Auger recombination, which is a three particle momentum exchange. In this, two electrons collide, out of which one recombines with a hole and transfers its lost energy to the second electron, pushing it deeper into the conduction band. So in this, you have two electrons colliding with each other. One electron loses its energy to the second electron and recombines with the hole, and the second electron gains that energy and goes deeper into the conduction band. So you have band-to-band generation recombination, which can be triggered by thermal energy or photons. Here the carrier states are completely free and the energy exchange is radiative, that is photon is emitted, and this is dominant in direct bandgap semiconductors. Then RG centers are due to trap states and they are sequentially bound and free. So within the trap state, the electrons and holes are bound, but within the bands they are free, and they are generally exchange energy using phonons or using thermal, and they are dominant in indirect bandgap semiconductors such as silicon. Then excitons are triggered using photons or electric fields. They are electrostatically bound to each other, resulting in a neutral state formation. They are dominant in low permittivity such as organic semiconductors. Then you have impact ionization and Auger recombination, which are triggered in high electric field regions. The carrier states are free and also have high velocity, and the energy exchange is kinetic, which is particle to particle. So the one particle transfers energy to another particle, and they are dominant. They are dominant where there is heavy doping or when a high voltage is applied. If you have a doubt, you can write in chat or you can speak. Now the role of material geometry, direct versus indirect band gaps. So we draw this using the EK space diagram, which is a plot of energy versus wave vector k, where k represents momentum. So momentum P is calculated using h bar k. So k can represent momentum. So in EK diagram, so if the valence band minima and conduction band valence band maxima and conduction band minima or on the same momentum line, they are called direct band gap, and if they are at different momentum lines, they are called indirect band gap. So here, indirect band gap, the conduction minimum, valence maximum align at the same momentum state, and electron only needs a change in energy to transition. So only electron needs energy to transition. Whereas in indirect band gap, where band extremes lie at different k values, a transition requires both a massive change in energy and a massive shift in momentum. So you also need to electron needs to change energy and momentum to go from conduction valence band maxima to conduction band minima. So the energy transition is done using photons or thermal, and the momentum transition is done using phonons. So energy versus momentum carriers. So the photon, which is the energy carrier, has a wavelength of approximately 10,000 angstroms, provides energy roughly equal to the band gap of silicon. However, its momentum is almost zero compared to the lattice. Whereas the phonons, which are momentum carriers, which are lattice vibrations spaced at, spaced at d approximately 5 angstroms for silicon. So the energy is merely thermal noise, which is in 10 to 15 milli electron volts, but the momentum, which is 2 pi by d, is vast because the wavelength is atomic in scale. So since the wavelength here is very small, it has a large momentum, but energy is very minimal. So, so photons are negligible momentum but high energy. Phonons are negligible energy but high momentum. Uh, So in indirect diagrams, you need two particles for movement, a photon for energy delta E and a phonon for delta K. So in material side, silicon band-to-band generation is extremely rare because it requires simultaneous interaction with two completely different species, a photon to provide the vertical energy lift and a phonon to provide the horizontal momentum shift. The statistical probability of an electron intercepting a photon and a phonon at the exact same time and position is near zero. So it needs a two multi-step transitions, which is why traps dominate indirect semiconductors. So because direct band-to-band generation requires an improbable two-particle phonon plus photon collision, an alternative path is required, and the solution is provided using RG centers. So RG centers act as intermediate parking states. An electron can gain energy to reach the trap, holds its position, and wait for a secondary momentum interaction to complete the journey. So in indirect materials like silicon, RG center based recombination generation dictate the effective electron and hole counts. So the continuity equation. So to track carrier counts out of equilibrium, we isolate a control volume and we calculate the effective total variation over time as the sum of competing internal and external mechanisms. So there will be spatial transport, which will be carriers flowing in and out via electrical currents. There will be internal dynamics, which will be internal generation and recombination events, and there can be external forcing, which can be any other external processes which are affecting the lattice. So you will have dn by dt total equals to dn by dt current plus dn by dt rg plus dn by dt any other mechanism. So then this results in multiple states. So in thermal equilibrium, the dN by dt total is 0. So every internal derivative results in zero net change. This is called detailed balance. So the internal mechanisms are still happening. It's just that their effective change on the total concentration is 0. So this results in dN by dt total equal to 0, and this is called thermal equilibrium. Then you have a non-equilibrium state where dN by dt total is 0, is non-zero. So the internal derivatives are also non-zero. So the light or voltage is actively changing the total carrier count in that control volume. Then you have non-equilibrium steady state where dN by dt total is 0. So the internal derivatives are non-zero. So the mechanisms are active but are perfectly counterbalanced. So each mechanism is not internally counterbalanced but counterbalanced by different methods like RG is so recombination and generation are not counterbalancing each other, but they are counterbalanced by the incoming current or any other third external force. So the takeaway is that a semiconductor out of equilibrium can still achieve stability. In a non-equilibrium steady state, the internal mechanisms like RG events and currents are highly active, they are non-zero, but perfectly counterbalance each other to maintain a constant total carrier count. So now we will model trap assisted recombination. So in a typical trap assisted state, you have valence band, conduction band, and the trap state. So the free free carriers in conduction band is called N, that are the free electrons, and in valence band they are called P, that are the holes. So and in when we come to trap state, we can say the capital NT is total concentration of traps, out of which NT is the small nt is the traps occupied by electrons, and PT is which are traps occupied by holes, or in other words, which are empty traps. So obviously, capital NT is equal to small nt plus PT. So the traps are mutually exclusive and finite. An electron taking a spot inherently means a hole or empty space is lost. So you have emission, which is generation. So where the electron is released from electron is released from the trap and going either go to conduction band or valence band. And similarly, it can take in an electron from the conduction band or valence band. So in emission for the electrons, the rate is proportional to small nt, which can be then written with a proportionality coefficient ENT. Whereas for emission of holes, the rate is proportional to PT, which can written as EPPT. Then for capture for electrons, the rate will be proportional to PT into N. So as it requires a free electron in the conduction band and an empty trap in the trap states. So it's proportional to both of them. So it can be written as by the proportional constant Cn PTN. Similarly, for holes, the rate will be NTP. which can then be written as Cp NTP. So the net flow equation with of RG mechanism only will become dN by dt is equal to En Nt minus Cn Ptn. So for electrons. So this is the rate of emission and this is the rate of capture. Similarly, holes, it will be dP by dt equals to EPPT minus Cp NTP, which is the rate of emission and rate of capture. So any change in carrier population is simply the physical difference between what the traps emit and what they capture. So equilibrium versus non-equilibrium dynamics. So at equilibrium, no external stimulus, everything is balanced, and although microscopic movement exists, but net rates are zero. So dN by dt is zero and dP by dt is zero. Whereas in transient non-equilibrium, system is shocked out of balance. Carrier counts N, P, NT, PT are dynamically shifting with time. So all of them are all of them are changing with time. Then we come to steady state non-equilibrium. So the flux has stabilized. Carriers flow constantly, but the internal trap counts are time invariant. So they are not changing with time. So the equilibrium anchor, step one, the assumption. We assume that moving the semiconductor slightly out of equilibrium changes the populations, but does not change the physical proportionality constants, that is En, Cn, Ep, Cp. Because the net change is zero at equilibrium, emission must equal capture. So for that we balance them at equilibrium. En naught, Nt naught equals to Cn naught, Pt naught, N naught. So that we get dNt by dt equals to 0. From then we can calculate each part. So En naught equals to Cn naught, Pt naught, N naught by Nt naught. Similarly for Ep naught, we can say Cp naught, Nt naught, P naught by Pt naught. So then we can write the emission coefficient in terms of capture coefficient. So this would make dN by dt equals to Cn Pt naught N naught by Nt naught Nt minus Ptn, and dP naught by dt equals to Cp Nt naught P naught by Pt naught Pt minus Ntp. So now we have converted it from a two constant equation to a one constant equation. So next we come to steady state recombination. So at steady state non-equilibrium, the internal traps states NT-Pt are locked in place. Their time invariant, so dNt by dt is 0. If traps aren't filling up or emptying out over time, then every electron that drops into a trap must eventually followed by a hole capturing that electron or vice versa, which means dN by dt must be equal to dP by dt. Since they are not staying in the traps, they are moving to the other band. So because the rates are identical, we can equate the two halves of equation 1 and solve for NT, which allows us to find the unified recombination rate R. So this so if we calculate that, we can get the minority carrier lifetimes, which for n-type material will be tau p equals to 1 by Cp Nt, and for p-type material, so in n-type material the minority carriers are holes. So hence we are talking about holes here. So that's why it's tau p. Whereas in p-type material, the minority carriers are electrons. Hence we are talking about tau n equals to 1 by C and Nt, where Nt is the total carrier of the trap states. So minority carrier lifetime holes means the typical time an injected hole will survive in an n-type semiconductor before hitting a trap and recombining. Similarly, minority carrier lifetime of electrons is a survival type of an injected electron in a p-type semiconductor before it recombines. Next, we come to mid-gap approximation, that is where Et is equals to Ei. So here the complex fraction Pt naught n naught by nt naught. So we must evaluate this complex equilibrium fraction utilizing the Fermi function probability of energy state. So if Et is close to mid-gap Ei, this will be equal to Gt Ni e per Et minus Ei by Kt. And since we are considering Et is almost equal to Ei, then Et minus Ei will become 0. So and in traps the degeneracy factor Gt is 1. So finally we get Pt naught n naught by Nt naught equals to Ni, and Nt naught P naught by Pt naught equals to Ni. So the massive complex equilibrium fraction simply collapse to Ni, which is the intrinsic carrier concentration. So this makes us our recombination rates very simple to calculate it. So the recombination rate becomes Np minus Ni square divided by tau p n plus Ni plus tau n p plus Ni. So where the Np minus Ni square is derived from the mass action law. If the system is at equilibrium, this is 0 and recombination stops. Whereas tau p and tau n are the minority carrier lifetimes, dictating how fast the system is allowed to process the recombination, where n plus Ni and p plus Ni are the dependencies on the abundance of free carriers in the system. And then we can have electron injection. So we have low level injection. So if we inject a tiny amount of excess carriers, delta n and delta p, into an n-type semiconductor where they are less than n naught, where n naught is the free electron carrier concentration at equilibrium. So the excess is a drop in the ocean compared to majority carriers. So that makes a so that would make that n naught plus delta n is equal to n naught, and so np minus ni square, if we calculate, it reduces to delta p dot n naught, and then the denominator and the n plus ni is again is very huge. So n is very huge compared to ni, so it will drop out to n naught. P and p plus ni is very small compared to n, so it will be negligible. So the numerator drops to delta p n naught, and the denominator drops to tau p n naught. So because n naught is massive, the entire bottom term collapses to just tau p n naught. So which leads to a recombination rate becoming delta p by tau p. So in low level injection, the recombination rate is entirely bottlenecked by how fast the minority carriers can find a trap. Next we come to depletion region. So we have a PN junction here. So depletion region is a region engineered to be swept entirely clean of free carriers. So there are no free carriers in the depletion region, so such that N is less than Ni and P is less than Pi. So the so in the numerator, np minus ni square, we have because n and p are both less than ni, so only the np will be negligible, so ni square term will remain. Again in the denominator, n and p both will be lost and only ni will remain. So the recombination will become minus ni by tau 1 plus tau p. So the negative sign here is critical. A negative recombination rate means pure generation. So since we have we have made it completely void of free carriers, so the crystal is desperately trying to generate carriers to reach equilibrium. So this is what we just studied. So by systematically tracking the physical routes of trap emission and capture and applying the strict constant of steady state accounting, a complex system of differential equations collapses into a single unified truth. So a semiconductor is governed by three fundamental objects: counting, which is the which which we studied last week, where we determine the carrier count from density of states and Fermi distributions. Next is dynamics, where we model carrier dynamics through recombination generation and quasi-Fermi states. And next is movement, where we calculate bulk movement via drift and diffusion mechanisms. So right now we are studying dynamics and we will make the bridge to movement. So visualizing the geometry of carrier capture. So the electron travels with thermal velocity Vth, which is derived from mVth square by 2 equals to kT by 2. So in time t, it sweeps a volume of Vth into t into A. So instead of a 3D maze, we can project the volume on a 2D plane. So now the capture of electron capture of carriers becomes a pure probability problem. What are the odds the electron lands on a projected red target sigma? So sigma we are considering as carrier capturing centers. So deriving the capture rate geometrically, so volume swept is Vth into T into A. Then we project it in 2D, so that becomes Vth into T into A into Pt into sigma, where Pt is the number of traps per unit volume. And so then we calculate capture probability, which is the projected target area divided by total area. So which is Vth into T into Pt into sigma. And then we can get the time derivative, which gives us the probability rate, which is Vth into Pt into sigma. And from there we can calculate the capture coefficient Cn. So our geometric rate dn by dt is Vth into Pt into sigma into n, which matches the traditional rate of dn by dt equals to Cn into n into Pt. So therefore the capture coefficient becomes Cn equals to Vth into sigma. So, so in dark, which is equilibrium, we have, let's say, an n-type semiconductor where Nd is 1 into 10 power 15 per centimeter cube. So we have electrons 1 into 10 power 15 per centimeter cube. Holes we can calculate using mass action law, which gives us 1 into 10 power 5 per centimeter cube. Then we can calculate the Fermi level for both using the EF minus EI, using N which get 0.29, using P we get 0.29 EV, so which is the same. Now let's say we eliminated and the light is generating 1 into 10 power 12 electron hole pairs. So the new N will be 1 into 10 power 15 plus 10 power 12, which is which remains 10 power 15, so it is virtually unchanged. And the P is 10 power 5 plus 10 power 12, which becomes 10 power 12, which is a massive increase of over 10 million. So now if we calculate EF minus EI using N, it is still 0.29 eV, but if we calculate using the new P value, it yields 0.17 eV. But a single thermodynamic system cannot have two different Fermi levels. So the solution is splitting into quasi-Fermi levels. So we are now assuming that there are two quasi-Fermi levels, one for electron and one for hole. They are not real Fermi levels, they are assumed Fermi levels under non-equilibrium conditions. So under non-equilibrium conditions, we abandon a unified Fermi level. Electrons govern their own statistical population via the quasi-Fermi level for electrons, and holes govern their own separate separate statistical population via the quasi-Fermi level for holes, which is EFN for electrons and EFP for holes. So in earlier case, we had EFN minus EI equals to 0.29 eV, and the here the EFP got shifted, so EFP minus EI is now minus 0.17 eV. So this diagnostic tool allows us to model highly energized non-equilibrium systems without breaking thermodynamic math. Now we come to drift transport, which is the band bending topography. So we are applying an external electric field E equals to VA by L, which bends the foundational energy bands. So the electrons seek lower energy. They literally roll downhill from a higher potential side, and holes seek higher energies. They float uphill through empty states in the valence band towards the lower potential side. So why electron and hole currents sum together? So the electron has negative charge, whereas hole has positive charge. The physical direction for electron movement is right to left downhill, whereas physical direction for hole movement is left to right uphill. So the conventional current direction for electrons would be left to right, which is opposite of physical flow. Whereas for holes, since they are positive charge, the current direction will be same as physical flow, which is left to right. So in both cases, the current direction is left to right. So because holes have opposite charge and move in the opposite direction, their mathematical signs cancel out. Both particle flow result in conventional current moving in the exact same direction, meaning they additively contribute to total drift. So drift current density equation is given using the total drift current density, which is current per unit cross sectional area I by A, which has the electron contribution and the hole contribution. The electron contribution is free and an electron concentration n multiplied by their physical mobility mu n through the lattice. Similarly, for hole, it is hole concentration multiplied by the mobility mu p through the valence band. And you multiply it with the q, which is the elemental charge, and you multiply it with applied electric field E, which is driving the system. So if we assuming low fields where carrier velocity responds linearly, we have Vd proportional to, so we know Vd is proportional to mu n and mu p. So for low electric fields, Vd will be proportional to E. So now if we integrate it across the whole device, so in microscopic you have lattice points which are filled with electrons and holes, and you have a movement across the band. So now we integrate it over the whole volume. So I dx is equal to integration q n mu n plus p mu p dv, which results in v the uh, I is equals to q n mu n plus p mu p into a dv by dx, which is given, which is our electric field. So this results in total current I equals to j dr equals into a, which is q n into mu n plus p into mu p into e into a. And so from here we can get our applied voltage. So from electric field we can make it from dv by dx. We replace the electric field into va by l, where va is our applied voltage and l is the length of the semiconductor. This we then convert put this we then put here. We get from here we can calculate va is equals to 1 upon q n into mu n plus p into mu p l by a into I. Now by Ohm's law we know that this part is our resistance, and we know that R equals to rho L by A. So this gives us our rho, which is resistivity, equals to 1 by Q mu n into P mu P. So we derived our macroscopic resistance from our microscopic properties Q n mu n P mu P. And from here we also calculated, we derived the Ohm's law. So the continuity equation is the ultimate governing law. So it takes into account counting, dynamics, as well as movement. So by combining our ability to count carriers, track their generation recombination dynamics, and map their bulk transport under an electric field, we possess a complete accounting budget for the semiconductor volume. This total budget is a master key to solving semiconductor reactions under any operating condition. So now we come to charge transport. So concentration gradients drive microscopic diffusion. So just as sweet scents diffuse through the air to be sensed away from a bakery, particles naturally migrate from high to low concentration. So you have a lower potential region and a higher potential region. So particles will naturally move from the low potential to high potential region with concentration gradient dn by dx. So for charged entities like electrons, diffusion acts as a self-induced drift. The presence of crowded charged particles locally lowers the voltage, driving the carriers towards uncrowded spaces. So to calculate, we first set a macroscopic 1D boundary from x equal to 0 to x equal to L, where L is given as VTH into T call. So that is given as carriers travel this exact distance statistically before scattering against the lattice. So VTH is calculated as KT by 2 equals to half ME star VTH square. So this gives us VTH equals to square root KT by ME star. K is our, so K here is our Boltzmann constant. T is temperature. ME star is a reduced electron mass, and VTH is our thermal velocity. So then L is the given as the distance traveled before by by a carrier before scattering with the lattice. So calculating the effective flux across the entire plane, that is, we calculate flux from L to R, which is given as N into minus L into VTH by 2. Then flux from right to left is given as, so half the carriers at minus L move right, none and none are, so none of them scatter before crossing x equal to 0. Similarly, from right to left, half the carriers move left, so half are moving right and half are moving left. So the effective flux at x equal to 0 will become n at n of minus L minus n of L VTH by 2. So which where n of minus L and n of L are concentration at the scattering boundaries. So we can then translate this into mathematical gradients by using Taylor expansion. So n of L is n of 0 plus dn by dx L, and n of minus L equals to n of 0 minus dn by dx L. So from substitution, the effective flux will come out to be minus dn by dl L VTH, and then L we know as VTH into T call. So effective flux becomes minus dn by dx VTH squared T call. So the driving force of the effective flux is exclusively the concentration gradient. So converting particle flux to electrical current, we have effective flux as minus dn by dx VTH square T call. So here the negative flux means that electrons are physically moving from left to right, which is down the gradient. So, and then so, so this is the individual movement of electrons. We multiply it with Q, we get the current. So J diffusion N, which is the diffusion current density, is given as Q dn by dx VTH square T call. So the double negative become, so negative flux into negative electron charge cancels out. The resulting electron diffusion current is positive. So now we studied drift in the previous slides and diffusion now. So now we can substitute VTH square equals to KT by M star into our current equation. So this makes it J diffusion comma N equals to Q dN by dx KT by M star into T call. And we recall that drift velocity is Vd equals to mu E, and mobility is Q into T call by M star. So T call by M star is mu by Q. So if we place that here, our drift current density becomes Q into KT mu by Q dN by dx. So we must understand that no electric field is applied here. We are only borrowing the relationship between scattering, mass, and mobility to simplify a diffusion model. So we can write this as J diff n, which is electron diffusion current density, into Q dn by dx, where dn by dx is the electron concentration gradient, and Q is elementally charged, and dn is our diffusion coefficient, which is kT mu n by q. So it encapsulates our thermal energy kT, carrier mobility mu n, and charge into a single constant, which dictates how easily carriers are able to spread. Now from here we can so from electron so we okay, for electrons we calculate. For holes, if so assuming that gradient is positive, so particles will move left, resulting in negative flux. But for electrons the charge is negative, but for holes charge is positive. So the flux and charge won't cancel out. So J diffusion P is equal to minus Q dP dP by dx. So this results in negative current. So the current here is moving opposite to the gradient, whereas for electrons current is moving with the gradient. So next, the Einstein relation, which is the balance of equilibrium. So at strict thermal equilibrium with no external voltage applied, net current must be zero. If any drift current exists locally, it must be perfectly counterbalanced by an equal and opposite diffusion current. So mu q and mu e must be equal to q dn by dx. This results in d equals to mu, where d is mu kt by mu q. So we equate that and we place our values. So we assume a Boltzmann distribution n equals to n naught e power minus phi by phi naught, where phi naught is kt by q. Therefore, electric field will be minus d phi by dx. Therefore, gradient will be dn by dx equals to minus 1 into 1 by phi naught into d phi naught by d phi by dx. So we place both electric field and gradient in this equation. So q cancels out with q, mu cancels out with mu, and so n cancels out with n. D phi by dx cancels with d phi by dx, which leaves us with dn equals to mu phi naught, which is equals to mu kt by q. So in the previous equation we had assumed dn as mu kt by q. Now we have derived dn as mu kt by q. So the total current is given as drift plus diffusion. So the total electron current is J drift n plus J drift n, which is Q Q n mu n e plus Q dn by dx. Similarly for holes, Jp equals to J drift p plus J drift p, which is Qp mu p e minus Q dp by dx. So in electron it is plus Qn, here it is minus Q dp. So we have two types of conduction: drift conduction and diffusion conduction. Drift is driving force is electric field, which is E potential difference, where diffusion is derived using concentration gradient dn by dx, which is basically crowding. The key kinetic parameter in drift conduction is carrier mobility mu, where here in diffusion it is diffusion coefficient d, and so which are both linked by each other using Einstein equation, which is mu equals to k q d by kt, or d equals to q kt by mu kt by q. So the electron current direction is opposite to field, and it down the gradient, which is high to low, and the whole current direction is with the field and down the gradient, which is high to low, but the charge is so but electron and hole have different charges, so therefore for drift their current direction is different. The resulting conventional current direction is same for electrons and holes in drift, but different for diffusion. So now we come to continuity equation, which is a complete accounting of semiconductor carrier dynamics. So which is synthesizing drift, diffusion, generation, and recombination into a unified mathematical blueprint. So we can create an analogy with physics with accounting. So in accounting, the current balance is given as deposits minus withdrawals plus interest earned minus fees. Similarly, for in semiconductor physics, the current in is your deposit, the current out is your withdrawal, the the generation is your interest earned, and your recombination is the fees. So the core takeaway, the continuity equation is simply a strict mathematical budget. It tracks the total rate of change of electrons or holes in a specific volume by accounting for every physical mechanism that adds or removes them. So first we define the control volume, which is A dx, where A is your cross-sectional area and dx is a small 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 length. So to understand this entire understand the entire device, we first isolate a 1D differential sliver of space. We then measure everything crossing its boundaries and every reaction happening within it. So the incoming current is given as Jn of x, outgoing current is given as Jn x plus dx. The since it's dx, we can assume the generation and recombination to be same in the entire area given by Gn and Rn. So raw raw carrier budget is so it can be written as dn by dt into a dx, which is the net change, the total rate of change of electron count strictly inside this specific volume element over time is given as dn by dt into a into dx, where a into dx is your volume. Then we can calculate the current, which is Jn into x minus Jn x plus dx by minus q into a. So current entering minus current exiting. We are dividing by electron charge to convert raw electric current into number of electrons, and then plus Gn minus Rn into a dx. So the net creation and destruction of electron pairs happening independently inside the volume. So now from we have to convert it from discrete boundaries to continuous gradients. We can do that using Taylor expansion. So assume the exiting current is just entering current plus the rate of change across the distance dx, which gives us Jn x plus dx equal to Jn of x plus dJn by dx into dx. Then we can substitute so Jn of x minus Jn x plus dx is minus dJn by dx into dx. So if we substitute this back into the equation, we can remove the volume A by dx. So this makes us our formula dn by dt equals to 1 by q djn by dx plus gn minus rn. Now we can now we can now we have djn, so we have to separate it into different parts. So Jn we know is drift current plus diffusion current, which is Qn mu n dot into E plus Q into Dn into Dn plus dx. So now we calculate, now if we calculate djn by dx, so in the drift we will have varying electric field as well as varying concentration. So we will have n mu n into d by dx as well as mu n E into dn by dx, and in diffusion we will have just dn into d square n by dx square, and the q is cancelled out because we have 1 by q outside. So when we substitute this expanded terms back into 1 by q dgn by dx, the charge q cancel out completely. So now our general, so this results in general continuity equation for electrons, where we have dn by dt equals to n mu n d by dx plus mu n E dn by dx plus dn square by dx square plus gn minus rn. And from here we can calculate our holes equation also. But remember, for holes it is the charge is q plus q, so and drift and diffusion oppose each other. So resulting dp by dt will be minus p mu p d by dx minus mu p e dp by dx plus dp g, dp square by dx square plus d square p by dx square plus gp minus rp. So now we have this complex equation. From here we can create a very simplified equation. So for that, first we apply a filter that there is no electric field. So this results in the drift term vanishing. Because electric field is zero, there will be the E term is also zero and d by dx is also zero. So both the drift terms vanish. Now second we assume uniform equilibrium. So there dn by dt becomes d delta n by dt, and then we assume recombination as for minority current lifetime only. So that makes R equals to delta n by d tau n. So our final equation becomes d tau 1 by dt equals to dn d square tau 1 by not tau 1 d square del n by d tau dx square plus gn minus del n by tau n square tau n. So which is solvable. From here, so now we can apply further further restrictions based on our conditions. So if we take case 1, steady state plus no light, which is just spatial distribution. So our base equation is d tau 1 d del n by dt equals to dn d squared del n by dx squared plus gn minus del n by tau n. Now we have condition as steady state. So which means the time derivative d del n by dt 0, and we have condition no light, which means external generation gn is also 0. So the resulting is then 0 equals to dn d squared del n by dx square minus del n by tau n. So which we can solve easily, which will give us del n of x equals to a into e power minus x by tau square root dn into tau 1 plus b e power plus x divided by dn plus square root dn into tau 1. So this is similar to our particle in the box solutions we had found in the first class. And this square root dn into tau 1 can be written as ln, which is called diffusion length, which is it represents the average spatial distance minority carriers can survive diffuse before completely recombining into the lattice. So case 2 is then uniform distribution plus no light, so which is just temporal decay. So we have uniform distribution, which means there is no gradient. So which means d squared del n by dx square term is 0, and we have no light, so gn is 0. So we just have d del n by dt equals to minus del n by tau n. So which just makes it tau n of t equals to tau 1 0 into e power minus t by tau n. So which makes us understand the meaning of tau n. So the an instantaneous population of carriers dying out uniformly over time, strictly governed by their lifespan tau n. Now the case 3 would be steady state plus uniform elimination. So steady state means d del n by dt equals to 0, and uniform elimination, so there will be no spatial gradient. So d square del n by dx square is also 0. But so the resulting will be 0 equals to gn minus tau n by del n by tau n. So then our del n is equal to gn equal to tau n. So we have a constant excess carrier level del n, which is equal to gn into tau n. So this is a sustained equilibrium. The total excess carrier population is simply the rate of generation multiplied by how long these carriers live. So the inflow, which is generation, is matched exactly by the recombination outflow. So from general equation, we by applying certain filters, we get three different types of states. One is our spatial decay, where del n x is equals to a into e power minus x by ln. Then our temporal decay, which is del n of t equals to del n of 0 into e power minus t by tau n. And then we have sustained decay, where del n is equals to gn into tau n. So now I will be so now I will be showing you some practice questions. If you if you get the answer, you can speak or you can write in the chat. According to the Shockley-Reed-Hall SRH recombination theory, why are recombination generation that is RG centers located near the mid gap of the semiconductor the most effective at facilitating recombination? Mid gap traps have the highest capture cross sections because they are physically larger than shallow donor or acceptor donor dopant states. The rate of both electron capture and hole capture are maximized when the trap energy level is close to mid-gap, balancing the two-step transition process. Mid-gap traps possess a negative charge that coulomбically attract both electrons and holes simultaneously. Mid-gap states are only active under thermal equilibrium and disappear under high-level injection. So the answer to this will be B. So HRS recombination is a two-step process. First, an electron is captured from conduction band to the trap, and second, a hole is from the valence band is captured by the same trap. Or in other words, the trapped electron is emitted to the valence band. If the trap is too close to the conduction band, it easily recaptures and re-emits electrons, making hole capture unlikely. If it is too close to valence band, the reverse occurs. Thus, mid-gap traps provide the optimal balance where the transition rates for both steps are maximized, making them highly effective RG centers. In the context of organic and low permittivity semiconductors, what is the physical nature of an exciton and why does its formation act as an effective loss in terms of charge transport? An exciton is a high velocity free electron that has undergone impact ionization, losing its kinetic energy. An exciton is a coulombically bound electron hole pair that is electrically neutral and therefore does not contribute to electric current unless dissociated. An electron is a lattice defect created when high energy photons collide with the silicon nucleus. An exciton is a type of trap state located outside the band gap that permanently captures majority carriers. So the answer to this is B. So an exciton is a bound state of electron and hole which are attracted to each other by the electrostatic Coulomb force. Because it is a neutral entity, it has no net change and cannot contribute to drift currents under an applied electric force field, though it can diffuse. Therefore, exciton formation represents a temporary or permanent loss of free charge carriers, unless an electric field or thermal energy dissociates the exciton into free carriers. Which of the following describes the microscopic physical mechanism of impact ionization in a semiconductor under a high electric field? High thermal energy causes atoms to vibrate so violently that they release electrons into the conduction band. A fast moving high energy carrier collides with the lattice atom, transferring energy to excite a valence electron into conduction band, creating a new electron hole pair. Two electrons in a conduction band collide and one falls to the valence band while the other gains all the energy. Excitons are split into individual free carriers species by the formation of lattice vibrations. So the answer is B. Impact ionization occurs under very high electric fields where carriers that are electrons gain substantial kinetic energy between scattering events. When such a high velocity carrier collides with a lattice atom, it can transfer its kinetic energy into a bound valence electron, ex- exciting it to a conduction band and creating new electron hole pair. This process can lead to carrier multiplication and avalanche breakdown. The concept of detailed balance at thermal equilibrium mandates which of the following conditions for any individual microscopic physical process in the semiconductor. The sum of all drift currents must equal the sum of all diffusion currents, but generation and recombination can proceed unbalanced. Every individual microscopic process must be balanced by its exact reverse process, that is, thermal generation must equal a thermal recombination, meaning each derivative contribution is individually zero. Carrier concentrations must change linearly with time to maintain a constant current flow. The Fermi level must split into two distinct quasi-Fermi levels to balance the electron and hole concentrations. The answer to this is B. Detailed balance requires that under thermal equilibrium, every microscopic process must be in exact balance to its inverse process. This means that band-to-band regeneration exactly equals band-to-band recombination, and RG trap-based emission exactly equals RG trap-based capture. Consequently, each individual rate term due to current, RG, etc. is independently zero, preventing any net macroscopic changes in carrier populations. Consider a semiconductor at room temperature T equals to 300 K, KBT equals to 0.0259 eV, containing a single trap level ET located at intrinsic Fermi level EI. If the equilibrium Fermi level EF is located 0.259 eV above EI and the degeneracy factor GT is 1, calculate the probability of a trap state is occupied by an electron at equilibrium. 1, 0.5, 0.99995, 4.54 into 10 power minus 5. So the answer to this should be C. The probability that a trap state at 80 is occupied by an electron is given by the Fermi direct distribution f of Et equals to 1 plus gt e power Et minus Ef by kBt. So here Et is Ei, so Et minus Ef is Ei minus Ef, which is minus 0.259 eV. Thus, this becomes e power minus 10. So this becomes 1 upon 1 plus 4.45 into 10 power minus 5, which is 0.999954. So option C is the correct answer. Which of the following mathematical expressions correctly represent the Schottky Reed Hall steady state recombination generation rate are for traps located at Et equals to Ei, where N1 equals to P1 equals to Ni. R equals to Np minus Ni square by tau P N plus Ni plus tau N P plus Ni. R equals to Np minus Ni square divided by tau N N plus Ni plus into tau P P plus Ni. R equals to Np plus Ni square by tau P N plus tau N P. R equals to Np minus Ni square into tau P N plus tau N P. So the answer to this is A. So the standard SRS steady state recombination rate is R equals to Np minus Ni square divided by tau p into N plus Ni N1 plus tau n into P plus P1. When the traps are located at the mid gap, we have N1 equals to P1 equals to Ni, which simplifies the denominator to tau p into N plus Ni plus tau n into P plus Ni. This is a cornerstone equation in semiconductor physics for analyzing RG processes. An N-type silicon sample Nd equals to 10 per 15 centimeter cm minus 3, Ni equals to 10 per 10 per centimeter cube, undergoes low level injection under uniform illumination, creating an excess minority carrier concentration delta P equals to 10 per 13 per centimeter cube. If the minority carrier lifetime of holes is tau P equals to 2 microseconds, calculate the steady state recombination R under these conditions. 5 into 10 per 18 per centimeter cube per second, 1 into 10 per 19 per centimeter cube per second, 5 into 10 per 12 per centimeter cube per second, 2 into 10 per 7 per centimeter cube per second. So the answer is be A. Under low level injection in an entire semiconductor, the majority carrier concentration remains virtually unchanged. So N is approximately N naught equals to Nd, and the recombination rate simplifies to R equals to tau p by del 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 p by tau p. So given del p equals to 10 per 13 per centimeter cube and tau p is 2 into 10 per minus 6 seconds, we have R equals to 5 into 10 per 18 per centimeter cube per second. A p-type semiconductor has an acceptable doping concentration Na equals to 10 per 16 per centimeter cube and an intrinsic carrier concentration Ni equals to 10 per 10 per centimeter cube. It is subjected to low level injection such that the excess electron concentration is del n equals to 5 into 10 per 11 per centimeter cube. If the majority carrier lifetime of electrons is tau n equals to 5 microseconds, what is the net recombination rate R of electrons? 1 into 10 per 7 per centimeter cube per second, 1 into 10 per 11 per centimeter cube per second, 2 into 10 per 17 per centimeter cube per second, 5 into 10 per 17 per centimeter cube per second. So the answer to this would be B. So similar to the N-type case, under LLI in a p-type semiconductor, the recombination rate is dominated by the minority carriers, which is electrons in this case, and is given by R equals to del N by tau N. So we have del N equals to 5 into 10 power 11 and tau 1 into equals to 5 into 10 power minus 6. So R will become 1 into 10 power 11 per centimeter cube per second. Which of the following statements correctly explains why semiconductor device physics focuses primarily on minority carrier lifetime rather than majority carrier lifetime? Majority carriers do not undergo recombination because they are too numerous to meet minority carriers. Under low-level injection, the fractional change in majority carrier concentration is negligible, whereas the minority carrier recombination changes by several orders of magnitude, making minority carrier dynamics dominate non-equilibrium behavior. Minority carriers have a higher charge than majority carriers, making them more sensitive to electric field. The majority carrier lifetime is physically always zero, as they recombine instantaneously. So we just studied about this. So under low level injection, the excess carrier concentration, which is del N equals to del P, is much smaller than the majority carrier concentration, but can be much larger than the equilibrium minority carrier concentration. Thus, the majority carrier population remains nearly equal to its equilibrium value, so no observable dynamics. While the minority carrier population experiences a massive relative increase, the transient return to equilibrium is therefore completely governed by how fast these excess minority carriers recombine, which is defined by the minority carrier lifetime. Geometrically, if a semiconductor cuboid has cross-sectional area L, depth L equals to VST, and contains empty RG centers with capture cross-section sigma and volume concentration PT, which of the following represents the statistical probability that an electron passing through this volume is captured? P equals to VTH into T into PT into sigma. P equals to VTH T PT sigma by A. P equals to A by VTH T PT sigma. P equals to PT into sigma. So the answer is to be A. The volume of the cuboid is V equals to AL equals to A VTHT. The total number of RG centers in this volume is N equals to PTV, which is PT A VTHT, and the total projected capture area is N sigma. So the probability of capture is the ratio of total capture area to cross-section area, which is given as P equals to VTHT PT sigma. An electron in semiconductor at room temperature has an average thermal velocity VTH equals to 10 per 7 centimeter per second. If the capture cross section of a deep RG center of for electrons is sigma n equals to 10 per minus 15 centimeter square, calculate the electron capture coefficient Cn. 10 per minus 8 centimeter cube per second, 10 per minus 22 centimeter cube per second, 10 per minus 15 centimeter cube per second, 10 per minus 7 centimeter cube per second. So the answer to be A. So the relationship between capture coefficient, thermal velocity, and capture cross section is given by Cn equals to Vth sigma n. So Vth is 10 per 7, sigma is 10 per 15, minus 15. So Cn will be 10 per minus 8 centimeter cube per seconds. Which of the following statements best describe the concept of quasi-Fermi levels in a semiconductor? They are Fermi levels of a semiconductor under strict thermal equilibrium where it is heavily doped. Under non-equilibrium conditions, a single Fermi level cannot describe both electrons and hole populations. Thus, separate quasi-Fermi levels EFP and EFN are defined to describe the populations of conduction and valence band independently using Fermi-like statistics. They are virtual energy levels located inside a conduction band that represent the average kinetic energy of hot electrons. They are energy levels that exist only in indirect bandgap materials during phonon interaction. So the answer will be B. So when a semiconductor is taken out of thermal equilibrium by light or by bias, the relationship Np equals to Na squared no longer holds. A single Fermi level cannot mathematically describe both carrier concentrations. To preserve the convenient formalism of Fermi direct statistics, we define two distinct quasi-Fermi levels, EFN for electrons and EFP for holes, such that N equals to Ni into E per EFN minus EI by KT and P equals to Ni into E per EI minus EFP by KT remain valid. Calculate the splitting of the quasi-Fermi levels EFN minus EFP in electron volt for a semiconductor silicon sample at T equals to 300 K. Take KBT equals to 0.0259 eV, Ni equals to 1.1 10 per 10 per centimeter cube. Under non-equilibrium conditions where the carrier concentrations are N equals to 2.25 into 10 per 15 per centimeter cube and P equals to 1 into 10 per 12 per centimeter cube. So the answer to this will be A. So the splitting of the quasi-Fermi levels is given by EFN minus EFP equals to KT into ln NP by Ni square. Hence, NP is 2.25 into 10 per 15 into 1 into 10 per 12, which is 2.25 into 10 per 26 cm minus 6, and Ni square is 2.25 by 10 per 20 cm minus 6. So this makes NP by Ni square equals to 10 per 7. So EFN minus EFP is 0.0259 into ln 10 per 7, which is 0.417 eV. An N-type silicon sample with Nd equals to 10 per 15 per centimeter cube is in thermal equilibrium at T equals to 300 K. EF minus EI is 0.29 eV. Under low level illumination, 10 per 15 per centimeter cube electron hole pairs are generated. Which of the following correctly describes the shift of the quasi-Fermi levels relative to the equilibrium Fermi level F? Both EFN and EFP shift by exactly 0.17 eV away from EF. EFN remains virtually unshifted from EF because N approx N naught, while EFP shifts significantly downward towards the valence band because P increases by many orders of magnitude. EFP remains unshifted while EFN shifts upwards by 0.29 eV. Both quasi-Fermi levels merge at the intrinsic Fermi level EI. The answer would be B. So at equilibrium, N naught is 10 per 15 per centimeter cube and P naught is Na square by N naught, which is 10 per 5 per centimeter cube. So under low level injection, N naught is equal to P naught is 10 per 12 per centimeter cube. So the new carrier concentrations are N equals to 10 per 15 and P equals to 10 per 12, which is a 7 orders of magnitude increase. So thus EFP shifts dramatically downward towards the valence band, reflecting the massive relative change in minority carrier concentration. Which of the following physical variables determine the determines the drift current density of electrons, which is J drift n in a semiconductor? The spatial departure of electron concentration dn by dx, spatial derivative of electron concentration dn by dx, the product of electronic charge, the electron concentration, electron mobility, and the applied electric field, thermal velocity of electrons multiplied by the cross capture cross section, diffusion coefficient of electrons multiplied by the permittivity of the semiconductor. So the answer to this is, so drift current is the flow of charge carriers caused by an electric field. For electrons, the drift current density is J drift n equals to Q1 mu n E, where Q is the electronic charge, N is the electron concentration, mu n is the electron mobility, and E is the electric field. In high electric fields, the drift velocity of carriers in a semiconductor ceases to increase linearly with the electric field Vd equals to mu and instead saturates. What is the microscopic physical cause of this drift velocity saturation? The effective mass of carriers becomes infinite at high electric fields. High electric fields cause the carriers to undergo frequent scattering with optical phonons, which rapidly dissipates their excess kinetic energy. Impact ionization creates so many carriers that they physically block each other from moving. The band gap of the semiconductor narrows, preventing further expression. So the answer to B. At low electric fields, the drift velocity is linear with the field because the energy gained by carriers is easily accommodated by elastic acoustic phonon scattering. At high fields, the carriers gain enough energy to emit optical phonons, which is inelastic scattering, which is a highly efficient energy loss mechanism. Consequently, consequently, further increases in the electric field do not increase the steady state drift velocity, leading to velocity saturation. Calculate the resistivity of a silicon sample at 300 K doped with Nd equals to 2 into 10 per 16 per centimeter cube donor atoms and Na equals to 5 into 10 per 16 per centimeter cube acceptor atoms. Assume complete ionization Q equals to 1.6 into 10 per 10 per minus 19 coulomb. Mu n is 1350 centimeter square per volt second and mu p equals to 450 centimeter square per volt second. Neglect minority carriers. 0.31 ohm centimeter, 0.23 ohm centimeter, 2.31 ohm centimeter, 0.93 ohm centimeter. So the answer to this is A. Since the donors outnumber sector, the sample is net n-type with donor concentration Nd minus Na equals to 2 into 10 per 16 minus 5 into 10 per 15, which is 1.5 into 10 per 16 per centimeter cube. Under complete ionization, the free electron concentration is N approximately 1.5 into 10 per 16 centimeter cube and P is negligible. The conductivity is sigma equals to mu and q, q and mu n. So it would have, if we had also considered minority carriers, then it would have been q n mu n plus p mu p. But we are neglecting minority carriers, so it's just q n mu n, which is calculated as 3.24 Simons per centimeter, and the resistance is 1 by sigma, which is 0.3086 ohm centimeter, which rounds to 0.31 ohm centimeter. What is the primary macroscopic driving force that causes diffusion current in a semiconductor, and how does it fundamentally differ from drift current? The driving force of a diffusion is the magnetic field, which aligns carrier spins, whereas drift is driven by gravity. The driving force for diffusion is concentration gradient of carriers, causing net movement from high to low concentration due to random thermal motion, whereas drift is driven by an electrostatic potential gradient, that is electric field. Diffusion is driven by the temperature gradient, while drift is driven by pressure. There is no fundamental difference. Both are driven by the same applied external voltage. So the answer to this would be B. Diffusion is a transport mechanism driven by the concentration gradient dN by dx or dP by dx, causing carriers to naturally spread out from regions of high concentration to low concentration due to random Brownian thermal motion. In contrast, drift is driven by an electric field voltage gradient acting on the net change of carriers, net charge of the carriers. Calculate the electron diffusion coefficient Dn in centimeter square per second in silicon at room temperature T equals to 300 K, kVt by Q equals to 0.0259 volts. If the electron mobility is mu1 equals to 1000 centimeter square per volt seconds, 25.9 centimeter square per second, 38.9 centimeter square per second, 10 centimeter square per second, 0.0259 centimeter square per second. So the answer will be A. According to Einstein relation, dn equals to mu1 into kt by q. Given mu1 is 1000 centimeters square per volt second and kt by q is 0.0259 volts, dn we will have 25.9 centimeters square per second. At a specific location in a semiconductor device, silicon device, at 300K, kBT by Q by equals to 0.0259 volts. The electron concentration is N equals to 10 per 16 per centimeter cube. Electric field is E equals to 20 volt per centimeter. And there is a concentration gradient dN by dx equals to 10 per 19 cm minus 4. If the electron mobility mu1 is mu1 equals to 1200 centimeters square per volt second, calculate the total electron current density Jn, which is that is drift plus diffusion. 38.4 ampere per centimeter square, 49.72 ampere per centimeter square, 88.12 ampere per centimeter square, 11.32 ampere per centimeter square. So the answer would be C. So the total electron current density is Jn equals to J drift n plus J diffusion n, which is Qn mu n E plus Q dn by dx, where dn is mu n into kt by q, which is 31.08 centimeters square per second. So the drift component J drift n will be 38.4 ampere per second, and diffusion component would be 49.728 ampere per centimeter square. So we add both of them, it becomes 88.128 ampere per centimeter square. Which set of assumptions is required to simplify the general electron continuity equation to the minority carrier diffusion equation d del n by dt equals to dn d square del n by dx square plus gn minus del n by tau n. Degenerate semiconductor, high electric field and high level injection. Uniform doping B. Option B, uniform doping, zero electric field, low level injection, and we are tracking minority carriers in where the equilibrium concentration does not vary in time or space. C, strict thermal equilibrium, zero generation and infinite minority carrier lifetime. D, organic semiconductor with excitonic transport and impact ionization. So the answer to this is B. So to simplify the general equation to the magnetic carrier drift diffusion equation, we require zero electric field equals to zero, which eliminates the drift terms. Uniform doping, meaning N naught and P naught do not vary in space, which so dn naught by dx is zero. Low level injection, which allows the recombination rate to be approximately linear as del n by tau n. And so we track just minority carriers, which are electrons in p type, so that dn by dt is equal to d tau del n by dt, and dn by dx equals to d del n by dx. What is the physical interpretation of the diffusion length ln equals to square root dn by tau n dn into tau n of a magnetic carrier in a semiconductor? It is the total length of the semiconductor bar. It is the average distance a minority carrier can diffuse through random thermal motion before it recombines with a majority carrier. It is the distance a carrier travels in 1 second under a unit electric field. It is the width of the depletion region under zero bias. So the answer to this is B. So the diffusion length Ln equals to square root dn into tau n represents the average distance an injected minority carrier can diffuse into a field-free region before it undergoes recombination with the majority carrier. It is a critical parameter for design in devices like bipolar junction transistors and solar cells. Thank you. This is all I had for today. Thank you for attending this session.